Hence it was as follows. Finally, a high voltage and short-circuited test was carried out, to confirm the winding is in a good health. As the next step, placed the stator into the motor housing as follows. Used a couple of following bearing for mounting on the both ends of the shaft. At the next stage, we chose the most relevant thermal overload cutout for the protection of motor to avoid being the motor burnt due to overcurrent flow. As I noted you, my objective is to run this motor at the rated current of 4 amps, and hence, I don't like to bring my efficiency down, while letting the motor to run at a higher current flow, especially more than 4.5 amps at 230 volts condition. Similarly, due to the voltage fluctuating, the current can be varied, and hence I'm trying to make this motor capable to run between 120 volts and 250 volts. So after the calculation, hope you remember that we have ended up our result with the B37U type top, which is to be cut out at 7.1 amps after a 16.6 minutes motor running. After that, the remaining components such as fan cover, terminal box, metallic base, end covers etc. have been placed, and later, it was sent for the final testing. Due to some restrictions and policies, I regret to inform you that we are unable to show off you these steps. Hence I will drop you the required evidences only for your reference about the final performance of our designed motor. No load current in amperes on the multimeter display. Current at the load of 0.9 horsepower instead of 0.75 horsepower. Here I tuned for the maximum load, where the efficiency remains at 90% and maximum mechanical load was 0.9 horsepower, and it ran at 3.28 amps. Hence the final specifications of the manufactured motor compared with the initial assumed specifications are as follows after an 8-hour long run. Characteristics under calculated, simulated and physically resulted conditions as follows. Supplying voltage for the all conditions was 230 volts. Power output required was 0.75 horsepower for the 3 conditions. Frequency was 50 Hz. No load current. In our calculation we imagined to run at 1.5 amps, and when it came to simulation it was 1.25 amps. But in real world it was 1.35 amps. Rated current at 0.75 horsepower power output. In our calculations, hope you remember, we imagined to run at 4 amps, and when it came to simulation, it was about 3.05 amps. But in real world, it is just 2.8 amps, and with a constant efficiency of more than 90% output, it ran up to 0.9 horsepower output, but at just 3.28 amps. No load speed. In our expectation, it was about 2990 RPM, where in simulation, it was 2998 RPM. But in real, it is about 2996 RPM. Rated speed. In our expectation, it was about 2900 RPM, where in simulation, it was 2960 RPM. But in real, it is about 2947 RPM. This is the advantage of eliminating the double revolving effect totally out. Permanent split capacitor. In our calculation, it was 20.8 microfarads, but hope you remember that we assumed it as 20 microfarads thereafter. Hence in simulation also, we were given it as 20 microfarads. But fortunately, in real world we found a capacitor of 20.3 microfarads. Power given, at the load condition. In calculations, it was about 920 watts, since our imagined current was 4 amps where the voltage 230 volts. But when it came to simulation, it was about 703.43 watts. But in real-world design, it is just 754.4 watts. Power factor, at the load. In calculation, it was 0.95, lagged, due to the assumption of 20 microfarads capacitor. Hence in simulation, it was about 0.922, lagged. But due to the use of 20.3 microfarads capacitor in real world, it was about 0.97, lagged, and if we had 20.8 microfarads capacitor, indeed it would be absolute 1. Actual power input, at the load. In calculation, it was 874 watts, where the simulation, it was about 648.89 watts. But in real world, it is just 731.7 watts. Capable power output, or can call as nominal power output, to keep 90% efficiency output. In our calculation, it was about 783 watts equals 1.04 horsepower. In simulation, it was about 557.78 watts, which means around exact 0.75 horsepower. But in real world, it is capable to run at 673 watts equals 0.9 horsepower. Power efficiency. In our expectation, hope you remember, my aim is to take 90% efficiency. Hence, after we used 20 microfarads capacitor, our efficiency in calculations was 89.58%, where in the simulation, it was 85.9%. But due to the use of 20.3 microfarads capacitor, in real world, the efficiency was about 91.97%. Tested duration is in real world, and 8 hours continuous run. Fortunately, since the practical capacitor had the capacitance of 20.3 microfarads, where in our mathematical calculations it was 20.8 microfarads, and even though we assumed it as 20 microfarads later, the power efficiency and the power factor has been closed to 1. If the capacitance of the practical capacitor were 20.8 microfarads, it had to be 1. Hence the conclusion is, even though I was trying to run my motor to supply 0.75 horsepower power output at 4 amps, mathematically, it is able to supply 1.04 horsepower at 4 amps, and in practical development, the motor was reached to supply 0.9 horsepower at 3.28 amps. Hence it is extremely capable to supply 0.75 horsepower power output for a current lower than 3.28 with more than 90% efficiency instead of my imagined 4 amps before the start of the design. So this is the end of our lesson of teaching you how to design an induction motor, starting from an empty hand to the physical development, and if you had been with us from the beginning of these episodes, definitely, you would have learned what you were expected to learn right now. So don't forget to show your support by subscribing to our channel on YouTube, and stay tuned with us further, since we have been thinking to cover a wide range of engineering applications, theories, and designs for your acknowledgement. Thank you for staying with us. See you again on another important session on I Teach You.